Not yet. I see if people are coming in for the 7 a.m. The 7 a.m. So it's not right. Leave it open.
I normally don't.
No, I didn't fly yesterday. You didn't? Why? You guys are just kidding us. Oh, weird. I'm not so sick like this. Hey, yes, you are. Most of you are. I just said you. Honestly.
I'm big work.
Yeah. I see you under
And then I was like, okay, good morning, everyone. We're gonna get started since we have a little bit from yesterday to finish up. And then we'll start on sling systems. Yeah, thank you with the doors. I think a couple of people are gonna still maybe come in from their 7 a.m. So we'll do just initial attendance and then I'll add anyone that comes back in. Okay, Abby. I just talked to an Allie outside and it's fine. Same names. Okay, Alex. Mute. Alex. Alex, who's Alex? Alex is not. Alex. Other Alex. Okay. Alan is back there. Okay. Charlie's in the back. Yes. Edwin is in the back of this. Evan both in the corners. Ethan. That side, Jay, not yet. Harper in the front, Jake. It's not here yet. Jeffrey. Right here, back door. Justin. Here. Kevin. Sorry, I was confused. Alex usually sits right behind you right there. Max. Here. Mitch. In the back. Ollie still, I don't think has ever showed up. Omar, right there. Otto, still not a person here. Why do I keep forgetting? Roman, yes. Samuel, yeah, back. Spencer in the front. Tiffany in the front, and Victor, yes. Yeah.
Yeah. No. Like.
In the morning every day I have to talk about the syllabus. So really simple today, it's supposed to be sling systems presentation. If you want to connect that with your Cessna training app, that's more about your airplane little section. And then daily checklist. Yeah, we went over today. If you have any questions about yesterday, we can start with that as well before we move on to sling systems. And then we aren't doing emergency hot seat until week 2. So we should be good. And then we all know that tomorrow we'll just kind of be finishing up anything we didn't get today or get to today, and then a little bit about aircraft documents and airworthiness, and then we'll have, it says group oral quiz. I think it's a quiz that you take with your phone. So we'll see what the quiz actually looks like, but it's not a big deal. This is Alan.
Yeah.
Usually you were seen there last time, so got that out. No, you're good. You don't have to worry about being late in the flight. I just want to mark you present. And then I think there's only a couple slides left of this, detonation and pre-ignition, so. Be pretty easy. Okay. Detonation, pretty easy to understand, uncontrolled explosion of the fuel air mixture. Rather than a smooth controlled burn like we want from our engine. So it generates like extreme heat and pressure inside the piston. It can cause major engine damage. So we do not want detonation. It has a whole list of ways that this can be avoided. Biggest one is ensure, like we talked about yesterday, or I ran through really fast yesterday with the, let's go back, the octane ratings. Biggest thing, like I said, like right at the end of class as we were leaving, is you always want to go up in octane rating and not down based on whatever your POH says. So we're at 100 low lead. We're also using 91 no gas mixture right now. So we always want to be, if we need some other type of fuel that's not available. I mean, 100 low lead is the standard in aviation, so you're going to be able to whatever other airport that you go to, if you need to refuel, you can use just 100 low lead. They like to put in avgas as like a efficiency, better for the environment, a bunch of other like business reasons for it. So it runs fine on 100 low lead, so that's what we would use. That's pretty much insured at all airports that you go to. So we use that. But detonation, when we're talking about how this can happen, is if you're using a grade that's lower, because we talked about that's the grade is saying how much compression it can withstand before it self-ignites. So you don't want less compression than your airplane's used to withstanding, or you don't want more compression than your airplane's used to withstanding. That's how you get uncontrolled explosion. So something about cowl flaps, we don't have that. That's usually like underneath the plane that you'd open. We have the cowl lean flaps, but those you're doing during fleet flight. A rich fuel mixture is another one. Shallow climb angle to reduce or to increase cylinder cooling. So we don't have, as you know, control of our fuel air mixture. We don't have a knob for mixture. So we just want to shallow our climb angle to keep that. That's why we have a cruise climb. So we know that we want to climb out for best rate of climb is 72, but you usually only hold that up until like you're about to either turn crosswind or you're leaving the airport. You don't want to hold that for too long. So there's something called cruise climb. They kind of make sure your cylinders are cooling so you're not keeping that heat in there. So high power steep climbs as well also can overheat and cause that. So detonation, pretty simple. After that, there's a little picture. Instead of a smooth push like it's showing, it's like a hammer pushing down. Not great for the engine. Pre-ignition is exactly what it says. So we're prematurely or premature uncontrolled ignition of the fuel air mixture in the cylinder before the spark plug fires. So it's basically the engine is working against itself in this situation because the piston will compress at the same time as the gas is expanding, because before the spark plug was able to spark the mixture, it had already ignited pre-ignition, which, completely puts off the timing of the engine. We saw that cool picture that, or moving picture that I like, that like shows it's always moving back and forth. So if you have pre-ignition, that's ruining the timing of the engine. So the causes are like residual hotspots. It's carbon deposits inside the piston. Sometimes there can be carbon buildups that because of extreme heat can ignite on their own. Same with the hotspot, overheating the engine, producing high operating temperatures. So, obviously you're losing power if your engine is not able to keep running correctly. If it's off time, you're going to lose power. The engine's not working as efficiently as it can. It's not getting that smooth burn every time. It's off time from the rest of the pistons that are moving. So also causes severe engine damage. Same thing. So kind of the same idea, a little different on how it actually works. Detonation versus pre-ignition, but both are pretty bad and we want to be aware of both so that we're not causing damage to our engine. This also should have been pretty self-explanatory in the King School too, so we feel like we got an understanding of pre-ignition and detonation. All right, move on to back to the slides. I think it's literally just taking me back to slim systems. Okay. Okay, so this presentation, the slideshow is created by, I'm not sure what his title is now. I think it's Chief of Training or Director of Training, I think, but our Director of Training is Andrew DeClue. You might see him around. He created this slideshow. He also has a masterclass video about sling systems that if you haven't found already in the Discord under the PPL students, you should be able to see all the previous messages that have ever been sent in there. I can also resend it myself if you don't feel like scrolling up, but it should be just like barely scroll up and you'll see a link to a YouTube video that says Sling Systems. That's a whole like hour-and-a-half video by Andrew DeClue. I would call that a masterclass. We are on day 4 of PPL here. We have a couple instrument students that are sitting in to listen, but this is day 4, so we're going to keep it pretty simple. We're trying not to overwhelm everybody with too much information. We can get into a little bit of it, but we want to stay on the more simple side, and then we have plenty of weeks after this to come back to systems and dig a little bit deeper. But if after this you want to go watch Andrew DeClue's video about sling systems, I would recommend it. He is doing a masterclass on, no, I'm not teaching a masterclass on systems. That's what I'm trying to say here. We are gonna start pretty simple, and then if you want to dig more into it, also helpful because at home you can just literally what I did with the video was like you have to just go back all the time. Like I'd watch one clip of it and I'd be like, I already forgot what he said, already didn't understand what he said. I'd have to go just immediately go back and replay exactly what he just said. So really helpful to go back on that and just listen to the same kind of explanation about what's going on. Also the slides are in the hub. You should have access to the Sling 2 system slides. I also think they're in like the flight training documents under slings like documents, but we can look at that later if you want this actual PowerPoint to it. So just a disclaimer, they're also a work in progress, as it says. There's also things that have been updated since it says February of 2022. So obviously it's been a while since they've done these, so I can update them a little bit on what's changed since then, but we want to go through our POH as well as our main source of information about our systems. So table of contents, I mean, we'll get to all of this, so we'll go ahead and get started with basic information about the Sling 2. I think you could just read this. A lot of this is not, you don't have to know this off the top of your head other than our power plant is a Rotax 912 IS/ULS. We're mainly, like I said yesterday, using the IS version of the engine because that's our fuel injected engine, and that's going to be on 95% of our planes. So there's a little, I think it has one here. Sorry, I'll go back if people are right. Yeah. Okay, so there's going to be like a little thing to remember all of it, but we'll just go through the slides, go fast on. Biggest part that we want to note on here, we're using the Rotax 912. Our max gross weight is 1320 pounds. This is a light sport aircraft limitation. This is probably the biggest limitation to training in slings is that it is a light sport aircraft. And right now they're trying to amend the category so that slings can fly. Slings are able to fly with more weight than this. We often do fly with more weight than this, and the limitation is just based off of what they're limiting light sport aircrafts to. So we need to know when we're doing our weight and balance later on that 1320 is our max weight when we're doing weight and balance. And then intended uses, obviously we're training in these airplanes, they're not intended for aerobatics. Pretty self-explanatory, I think. Then basic information about our engine itself. We'll get into all this specifically in, I think the most helpful is to look at this right here. So the little acronym they have is RANOG 4. So RHANOG 4 to remember all of the basic key information about the Rotax. So R for Rotax, the Rotax engine itself, the 912 ULS versus IS. H for horizontally opposed, which we talked about yesterday. Horizontally opposed mainly in the sling to save space, so we don't have such a tall engine. It keeps us aerodynamic. That means that 2 cylinders are on either side, facing away from each other instead of stacked. I think in cars there's also a V shape. I don't know anything about cars, so no horizontally opposed. A for air liquid cooled. Air cooled from the outside air that we're taking into our air inlets, liquid cooled through many different types of liquid. Do we know what types of liquid are cooling our engine? Sorry, coolant. Coolant is one of them. Then we can also count oil is also a liquid that's cooling. And then people also count fuel as a cooling for our engine because it's constantly running through our fuel system. So that's also cooling as well. So, but mainly oil is cooling, and we have coolant that's cooling our cylinder heads specifically, but we'll get into that in the oil in the coolant system. And for naturally aspirated, does anyone know what naturally aspirated is? So yes, not turbo, but
Basically means you're using the air that's coming in to make your power.
exactly. So that's why we have a bunch of air inlets in the front of the plane. We have nostrils in the front, and we have on both sides of the cowling. You're probably doing a visual check to make sure those are clear on those air inlets on the side. All that's taking in ambient air coming in from the outside. So naturally aspirated with outside air. Oil is our oil system is dry sump, which means forced lubrication. In other planes, wet sump means that you have like a pan in the engine. Dry sump, forced lubrication means we have that tank, right? So when you open the cowling, you see our oil tank. You probably took it off and they showed you how to stick and grip the engine and all that. So that means our oil is contained inside a tank and then forced through pumps to lubricate around. So we keep our dry sump oil system. And then gear reduction, I think we'll get a little more in a specific slide, but we can go ahead and talk about it now. Gear reduction means we have a gearbox. So we have, when we talked about the crankshaft being connected to our prop in the front that spins our propeller, we have a gearbox in between our crankshaft and our actual prop that's spinning. It's used to slow down the propeller. So if anyone's flown in another plane before, which it seemed like maybe a couple people went on Discovery flight, but maybe you didn't notice initially what was happening with RPMs, but the RPMs of other planes are much, much lower. Like our cruise a lot of time is around 5,000 RPMs. This is not normal in other planes. They're about 2,000 in other planes. So we have a gearbox because we want the engine to run at such a high RPM to get more power. That ends up it's gonna, if we didn't have a gearbox, it would spin our prop so fast it would break the sound barrier. Essentially, it would shatter the prop itself. It can't spin that fast. So we have a gearbox to slow down the propeller but keep that high RPM. So it converts the crank RPM from the crankshaft to prop RPM, propeller RPM. It's slowing down, and I think they'll have a slide on it. Right now, we're just in the beginning, so if you want to be fancy and know the ratio, it's a 1 to 2.43 reduction. So for every one spin of the prop, it's 2.43 crank RPM. So we're getting a lot of power from our prop, a lot of power from our crankshaft, but in order to slow down that prop, we need a gearbox so that we don't break the propeller with how fast we're making it. So then 4 substitutes for 4-stroke and 4-cylinder. To remember, we have a 4-stroke, which we talked about yesterday, 4-stroke system, and a 4-cylinder engine. So does anyone need a second to finish writing this down, or we're good? Good? Okay. Wow, lots of words on here. I think we mainly went over all this. If you want to know, the manufacturer is the airplane factory. We know we went over it's a light sport aircraft, has a light sport aircraft certification, which means it has a special airworthiness certificate, which I think we'll get in tomorrow when we talk about airworthiness documents, but just know that it's a light sport aircraft. This specifically has a little list at the bottom of exactly what the panel is made out of. It's all Garmin, I think. Yeah, all Garmin. We went over the G3X at that big screen yesterday. We also have the GTN 650 that's certified for IFR flying, certified GPS. We have a Garmin autopilot panel, which I think you've seen in the plane because you're using a lot of times those autopilot panel knobs to turn your heading bug and your altitude bug. Yeah. They're shipped over from South Africa and they're put back together and certified at French Valley, which is a fun airport to go to across the mountains if you ever want to do a cross country with that. But this is just general information for your knowledge. We'll get into all. Okay, here's the meat of what we need to learn today. So first, we're going to start with the IS, the fuel injected system. So this is our main focus today since so many of our planes are fuel injected. So we'll take special attention, and I think at the end is where they add in a little bit about the ULS, but we're doing IS today, fuel injected system. So this is our electrical system diagram, simplified diagram for today. So what do we need to know? The basics of the electrical system is this diagram. Don't right now overcomplicate it from this. So you can see it starts with, it says internal generators. It's mainly one generator that is split for 2 different purposes. So I'm going to show you what the actual generator in the plane looks like, but just know we have generator A, generator B, essentially they're the same generator altogether. They're just doing different things, running the power different places. So we have generator A and B up here at the top. Those send power to what we call rectify regulators. It does exactly what it says. I think there's a slide next that we'll talk about what that means, but it rectifies and regulates the power that's going through. That means it's going to change what's coming from the generators is called alternating current, and it's going to rectify that current into direct current that goes to our ECU and our battery. So rectify regulator from the generator A is going to power the ECU. Who remembers what the ECU stands for? Engine control unit, perfect. And our internal generator B goes through the rectify regulator and powers the battery. It's this simple. Don't make it more complicated than this right now. Generator A and B, rectify regulators, ECU for A, battery for B. They have a thing down here for don't confuse the lane lights with the electrical system. We also, I'm sure you've seen, have lane A and B switches. We'll get into what the lanes are, but just right now, as a precautionary, those aren't generator A and B. Those are lanes A and B, and we have generator A and B for our electrical system. So I'm gonna keep going on this. I'd rather look at the picture, I think. So yeah, 2 internal generators. It's one dual system combined into one unit. I think there's better pictures on here. I'm sorry if anyone's writing down the words, but here in the engine is what our generator looks like. So is there a better pic here? Perfect. So we talked about right here in the middle, here's our crankshaft. We talked about how it's turning our propeller in the front. Here's our gearbox right here. Here's our propeller. In the front here, it's turning our propeller. It's also turning a magnet inside our generator back here that supplies our power. That's what produces power. And we'll go over what exactly happens. But our generator is back here behind the crankshaft, and it's also turning the generator. Here's a better picture. So the generator is made up of a stator system. So stator is it's a ring of stators that they're all basically each one of these little things are magnets wrapped in copper wire. And then what's turning by the crankshaft is a larger magnet. The crankshaft is turning a magnet that runs over all of these other magnets that are wrapped in copper wire. And this is what produces power. Basically, the heating that's created by running these magnets over each other is what's creating energy, producing power for our engine and our battery. So stator system, I think that's what all the words back here were. Yeah, the ring, 24 stators, not super important to know right now how many, but it's a ring of stators like it showed, magnets wrapped in copper wire. Then you have a bigger magnet in the middle that the crankshaft is spinning that runs over all the other magnets. And when the crankshaft spins, the magnet in the middle also spins, and then that spinning of magnets on top of the other magnets is what's creating power. And it's sent that power, like we said, off to the rectifying regulators and then off to the ECU and the battery. Does this first part make sense? Any questions? Yes.
Said when the power from the stator is sent to the rectifiers, it's turned from alternate power to direct power.
Correct. I think there's a slide. If anyone doesn't have any more questions, we'll get into perfect. Yes. And I think there's a picture. Perfect. Okay. So it's basically oscillating two directional current versus one directional current. So all of our batteries are powered and charged by direct current. So they have these rectifying regulators to switch to rectify the current from alternating current coming from our generator into direct current, which can power the ECU and all our batteries. You don't need to understand any more about currents than this. Anything that you explain is going to be the rectifying regulator converts AC current to DC current, alternating to direct current. I think that's about it if we understand this. Then, yeah, they convert the power coming from the generator for alternating current to direct current. And most equipment on the sling is powered via direct currents. So this is why we need the rectifying regulators to make sure we have the correct current to power basically all our batteries. We have a couple batteries in the sling. And they're located, I think there's a picture actually what they look like. Perfect. So inside, this is going to be the most familiar picture, might be this one down here of regulator A. When you open the left side cowling, you're gonna see this kind of gray box with the fins on it right here. The fins are just to cool the regulator over here, but you'll see this like right as you open that side. It's off to the right, and then you'll look down, you'll see your exhaust pipe and your cylinders and all that. So from the side, this is where regulator A is, and then right here in the middle, and here's another picture of it, is the fuse box. And then on the other side, planted back here, is regulator B, and it is the same regulator. They just put a fin like system on here to cool it down. But B is over here on the other side. So there's also, through all this, has anyone seen the engine that they have just sitting out there with all the parts labeled? That's super helpful. That was only introduced like at the end of my training, that they made that and put all the parts. I didn't have that during private, but super helpful because all of this seems very imaginary to me, just looking at like 2D pictures for a while and then trying to figure out what in the plane I was actually looking at was really hard. So when you have the time after this class, go look, sit down with that engine, run through, there's all label on it, run through all the labels and figure out exactly what everything looks like. We have a couple helpful pictures in here. We have a couple unhelpful pictures in here. When I looked at it last night, I don't even know what they're trying to show you in some of these pictures, but this is very helpful. You know exactly what you're looking at when you open the calendar. Nice. Okay, ECU, engine control unit, we already went over that. So this is the source that powers the engine. We talked about yesterday how in most planes, when you lose your electrical source, you still have your engine, and how that's not the case for slings, because we saw that generator is powering our ECU. Our ECU is what's powering our engine. So the ECU, I think it says on there, details later on, but the ECU is powering the three most important things that are controlling our engine. It's the spark plugs, the fuel injectors, and the fuel pumps. It says they'll have another slide on here, so don't worry if you didn't write that down right now, but it controls all of those through, like I said, sensors that are taking in all sorts of information on air density and pressure and temperature. And the computer, like I said, ECU is the brain of the engine. It's controlling all of this through sensors and figuring out exactly how much fuel to inject into the combustion chambers to create the exact amount of power that we're asking for in any condition. So yeah, monitoring a slurry of sensors that calculate performance and position and error-free operation. So it says we'll get a little more into it, so we'll keep going on this. Batteries. So we have one main battery, it's a 12-volt battery in the engine compartment. It powers the airframe as well as charging two backup batteries. So when we're talking about back to the original simplified drawing, and one generator A side is powering the ECU and generator B side is powering the battery. When I talk about ECU is controlling those three things, battery is powering everything else. Battery is powering the main battery that's charging, it's powering everything else in the plane. So when we're talking about the battery, it's literally powering everything else. So we'll start with the second battery is the G5, that little box in the middle that also shows you a PFD, a primary flight display. That little has its own, it says about 4 hours. I don't think that's actually accurate. It's probably more about 1 hour. It will tell you when you turn it on, but it has its own internal backup battery. We use this a lot when we're doing partial panel and instrument. If you lose your flight instruments, the main screen, then you have this little G5 in the middle that has its own backup battery. So you can turn that on if you lose power, and it will power itself. And like it says, during normal operation, the plane's main battery is also charging the G5's battery. And the last battery is for the Garmin 3X that we talked about yesterday. And it's marked, that's this backup switch on our plane. So that's a backup battery that's always being charged in the plane by the main battery. So someone asks you, I think this is like a trick phase check question that people use a lot. They'll ask you, how many batteries does this thing have? And the main answer is to say 3, because we just went over that. But some phase check instructors like to be a little tricky, and they'll say it's actually 4, because our ELT has its own battery as well. Our ELT is our emergency locator transmitter. I think I only talked about, I don't know if the other guy who did the pre-flight talked to you guys about this, but I told people I was doing a pre-flight with, it's a little switch in the plane on the right side, like right in front of where your instructor will sit. It says ELT on it. It's like a light switch looking thing. That's our ELT. It technically has its own internal battery. If you get the trick question, then feel free to use the trick answer, because that has its own battery as well. And that's how we for emergency locator transmitter, you turn that on if in an emergency you need to do an off-field landing. That sends out a signal. It's basically actually an alarm to all all comms over everyone in the area that says there's been an emergency, and it sends out signals so they are able to locate your plane. If you land in a field in the middle of nowhere, they will be able to find you and send emergency services. So it's important in an off-field landing checklist to turn that on. Important to tell someone if you accidentally flip it on, because it does not automatically go off. And just because you flip it off doesn't mean it's done transmitting the signal. So tell your instructor if you accidentally hit it, because you will start up the plane, you'll put your headset on, you'll realize that overall the comms, it's beep, beep. And you're like, what's going on? It was you, because you turned on the ELT switch. So tell somebody, they have to tell ATC, someone let ATC know to turn it off or something like that. I've never had it happen, but let someone know if you accidentally hit it. But that's where that extra battery is. Real answer is 3. Yes. Yes. That's why it's got its own separate
That's
battery.
like replace.
Yeah, there's actually, when we get into inspections, part of the inspections is the ELT inspection. It needs to be done. There's certain inspections on the battery itself that charges it, and you have to check that the ELT, there's times that you can actually flip the switch to check it. That has to be inspected, that it's actually working. But we will get into that about when you have to inspect it, but yes. That's part of the inspections we have to do on the plane. So we'll get back to, this is our electrical system for the ULS. Okay, it's going through both of them at the same time. So also simplified system for the ULS. We still have our generator in the middle. This time it's split where half of it with an N, that's for main generator, and then the other half is split into A and B. So the main half of the generator goes through a rectifier regulator to charge the main battery in the ULS. And then the other side for A and B each has powering a CDI-A and a CDI-B. We remember what CDIs are. Yes, Yeah.
They're the replacement for magnetos.
exactly, yes. They're kind of like a modified magneto for the sling. They both, CDI controls the spark plugs the same way the magnetos control the spark plugs, that mechanically times to send the signal to the spark plug to ignite. Basically a magneto system, yes.
And they both control one on each still on your head, right? Just like the
Yes, exactly. Just like the magnetos, it's split so that if one fails, the other still has control of all the cylinders through one connection. So same thing on both of those. Yeah. Do a little drawing of this to remember. You might be asked about this in phase checks in the beginning, just so you have an idea. A lot of the questions will go towards injected or IS engines, and the IS system altogether, but pretty simple on this side. So yeah, I think this is all the words that goes to what we talked about. It's technically 3 parts of the generator, one system itself. It's in the same place as the IS in the back of the engine. Yeah. It's also, just because we're talking about just because I remember, because they put alternators on here, our POH does reference alternator instead of generator. The way they use it is the same. Don't be confused, like I thought we had a generator, but it says alternator. They're talking about the same thing. It's a generator. They just use the words interchangeably for some reason. In the POH, even in the new POH that they just released. So just a side note, don't be confused if you're reading through the POH and it says alternator or alternators A and B, that means generator. It's the same thing when having to do with slings. So same thing with, I'm trying to read through all the words that they put on here. Yeah, generators function the same. as what we just covered for the IS, the fuel injector. And there's no documentation that has a set number for the stators. And the ULS, I think they pulled 24 stators from the Rotax manual, which is also available in the Sling documents if you want to read through that. But again, the number right now is not really important. It's a ring of stators, like we talked about. Little magnets wrapped in copper wire, big magnet gets turned over all the other magnets that creates heat, which creates power. Okay, carburetors for the ULS. It's back to, I think, your question yesterday on do we have carburetors in the ULS? So we have special carburetors in the ULS. Again, it's like a modified, just like we have a modified version of the magnetos, we have a modified version of carburetors. So what it's talking about here, we have what we call constant depression carburetors. They use air pressure to adjust the fuel. Is there another picture? Yeah, well, it's covering half the words, but it uses this is getting a little bit far because we haven't gone over it, but it's kind of like altimeter. The way it went over in Keen School, it's similar to how an altimeter works with the aneroid wafer that compresses. Does anyone know what I'm talking about, or is this all way too far ahead? Anyone? Okay, way too far ahead. Okay, so there's the way the altimeter works is there's like a little wafer inside that either compresses or expands based on the surrounding air pressure, and that air pressure has to do with the outside air pressure. So we know as we climb or as we descend in the plane, our air pressure changes based on lower pressure, higher, more pressure, closer to the ground. So it's moving that like wafer up and down or compressing and decompressing. We'll obviously have a whole lesson about how that works, but so as the outside air pressure changes, the needle, just like we talked about the needle yesterday in the regular carburetor, instead of having the needle be pilot controlled in the carburetor and the constant depression carburetor, the needle is controlled by air pressure. So just like we're talking about, as you climb into the lower pressure air, that's going to make the less fuel. It's just like leaning and enriching. So it needs less fuel higher up. So it's going to move that needle down and give it less fuel through the system. Does that sort of make sense? It's instead of us controlling the needle in the regular carburetor, we have a constant depression carburetor controlled by outside air pressure that moves the needle itself. It's mechanical, so we don't have any control over it. It's calibrated by our mechanics. I think every annual that it gets or something, so there's no way to change it, and it does it all by itself, just like most of the Sling systems control all by themselves. I think that's yeah. Oh, they're talking about, okay, so the throttle cable on each carburetor has a spring, so that a lot of the times the throttle cable is there, so if the throttle cable breaks, it will go full power. Because it's important, I guess I need to point out, there's two constant depression carburetors in the ULS. So instead of one carburetor, we have two constant depression carburetors, again for redundancy. And one of those carburetors, those CD carburetors, controls two cylinders. So they each have split into cylinder 1 and 2 and 3 and 4. I don't know how it works, but split into two different cylinders. It's the same with a failsafe on the throttle cable on each carburetor. Since there's two, they had to make something where if you have one, there's a chance now with two cables that one can break and one still works. So if it goes immediately full power, now your engine is off completely. Now it's running on half full power on two cylinders and no power on the other cylinders. So they have a fail safe. If it breaks, it has a spring, so it won't work half and half now that you have two cables. But that's what it's talking about. So two constant depression carburetors in the ULS. They each are controlling or each leading to two cylinders, and It's using air pressure to change the needle and determine how much fuel it needs. Let me know if anything's confusing so far. The ULS is the most confusing to me. A lot of the times you'll learn about it right now and maybe not look at it again for a long time. So yes.
At the bottom, it said, you're choking,
Now, what does it say?
I forget, is that R or R? Cause I think that's. Careful.
Yeah, I would assume that says art. I don't know why the picture's on top of the words. I didn't make this, so I can't tell you for sure what it says, but like you said, I would assume it's art because they're making a point to say unlike most art.
Yeah.
So. To tell them to try to do something with that picture, but. Like the IS, the ULS has one main battery, also a 12-volt battery. And also it is charging any built-in backup batteries. So same thing with the G5. And its backup battery is constantly charging, and same thing for the EFIS backup battery that's charging the Garmin G3X. Yeah. Okay. EMS is talking about engine management system. It's a little confusing when we have an ECU, engine control unit. A part of the EMS engine management system is the ECU, the engine control unit. So they just want to let you know, I guess, with this that the EMS is controlling fuel injection and ignition and fault detection, and it manages the generator's power. And parts of the engine management system are sensors and actuators, and the ECU itself, and then wiring harnesses. Really, this is not super important. We need one. ECU is super important. Like we talked about, the generator A and B are not the same as lane A and B. We want to go through that again, make sure we're understanding that. So lane A and lane B are, it's basically two ignition systems work together like a computer deciding what's the best use of power. So lane A or lane B is capable of taking over control and regulation and monitoring the engine. So in normal operation, both lanes are on, both switches on, and then the engine is being controlled like we talked about in the diagram by generator A. So it's also controlled by lane A and lane B. So that, okay, is there a better picture of this? I don't like all these words. Okay, this is better. So we're talking about lane A and lane B have control. We talked about they're controlling the spark plugs, the fuel injectors, and the fuel pumps. So that's what the ECU is controlling. Spark plugs, fuel injectors, fuel pumps. So when we're talking about normal operation of the lane system, each lane in an ideal world is controlling half. So we have lane A is controlling 4 spark plugs, 4 fuel injectors, because you have 2 for each cylinder, right? So there'll be 8 total. And then spark plugs, lane B, 4 and 4. The problem with the ECU is you won't know what each lane is controlling. Ideally in your head, just think of it as it's split into 2, but really the computer is there to decide how much lane A is controlling and how much lane B is controlling. And it can change the number of spark plugs it's controlling like this. It can change how much each one's controlling based on whatever it decides. That's the brain, like I talked about, the brain of the engine. It can be any combination, like it says, and the pilot, us, will not know exactly which lane is controlling how much of spark plugs and how much fuel injectors. Like it's saying, normal operation is half and half, but it changes based on so many factors. It's not super important that we know, obviously, because we're not going to know which one it's controlling, but that's why you're never going to touch the lanes. Ever, ever, ever. In flight, you're never going to turn off either one of the lanes, unless one of them is turned, the light is on and flashing, you recycle, you turn it off for a second and turn it back on, and that's what it means to recycle. You're never fully turning off one because you don't know what is being controlled by that lane. That's the main idea that we're trying to get here. The lane can be controlling half and half, it can be controlling all and none. But we don't know, so we will never ever touch the lanes or turn them off in an attempt to get the engine to turn back on or run better or do whatever. We don't know, so we will never touch those unless, we'll talk about lane lights in here, but you can recycle them, meaning turn them off for a second, turn them back on. But you will never ever ever turn them off unless you're on the ground trying to turn the plane off. We'll go back to what they're talking about back here. Yeah, ECU automatically selects a lane to control the engine. And it's pulling all this information from sensors. So we'll talk a little bit more, I think, about that, but this is made. Yeah, I think this is all. I'm gonna move to. Yeah, it's the same as, okay, if now we have a single lane working, so now lane A is taking all the spark plugs and all the fuel injectors, and the engine's running as normal because we don't know that lane B is not taking any of those. So if we, for some reason, were to turn off lane A, we've lost our entire engine because it's controlling all of those at once. Does this make sense? The lane system is confusing, especially coming from a different plane or how the King School is explaining it, but yes.
You're,
Yeah.
where you do this test return.
Yeah,
Don't both of those control a little bit different systems? So like, let's say for this example, you only have lane A.
when you see
certain ones-
failures,
Yeah, so certain ones won't work via
Yeah.
lane A, certain ones work via lane B.
yeah. It, for the run-up, you'll probably see that when you fail lane A, you'll see that it X's out, like it shows a failure on the, it's the oil pressure
Yeah.
for lane A, and then lane B is oil pressure and oil temperature on the failures. So this has a little bit to do with, that's like the equilibrium that's trying to hold, like it says like 4 and 4.
Yeah.
But the main idea they want you to take away from this is that's the idea of how it's working, but for whatever reason, if the sensors decide to change over, then you're going to have one lane taking all the load and then the other taking none. So they just want you to know that, to expect that both of them are working together, but never expect that one is gonna be able to be failed or turned off. You're going to see that indication every time you do the run-up on those failures. But I don't have more information on exactly why they're putting the failures on those two instruments and not the others. You have, I mean, you're failing half of the engine's capacity when you do that,
Yeah.
supposedly, because they're supposedly taking 4 and 4.
Yeah.
So that's why you're looking for an RPM drop on both of those, just kind of like magnetos, the same way
Yeah.
you're looking at it. But I'll either have to get more information from Ant, he doesn't cover this in his video either, which I think he watched as well. But yeah, I don't have exact information on what the sensors are specifically doing and how they're changing the laning. But I can figure that out. And I'm trying to keep this as simple as possible today, since it's a lot to do all at once. Like we said, lane checks, like we just talked about, and RPM drops. You're cycling in the run up when you turn it off and on. And when lane A is turned off, like we just said, you'll feel a jolt because you're losing, like you're losing everything that's controlled by lane A. So run-ups are performed in eco mode. By turning lane A off, you lose eco mode. That's why one of the indications when you turn it back on, I don't know if everyone does this, but I do this in the run-up. When it turns back on, you look for that lane light to be extinguished. So you have the no more lane light. You look for eco mode to come back on. and the RPMs to back to increase. Yeah, lane B, you don't feel a jolt because the plane is able to turn eco mode back by itself. And the RPMs pretty much stay exactly where they are. A lot of this is a little more advanced than we need to know. We just need to know what the lane checks are doing and why the RPM drops when we're checking. We can come back to this later on once we understand everything else. I'm not sure what this is supposed to be showing. These are the fuel pumps. This isn't a great picture. I think I'm gonna move on, but we have more pictures and an actual picture of what the fuel pumps look like, but this is from the road tax manual, I think, or the POH. There's the two fuel pumps. We haven't even talked about the fuel system yet, so I'm not sure why we're getting to see fuel pumps. Fuel selection. I'd also like to start with the diagram, but I guess we're starting with the fuel selector. So we've all seen the fuel selector in the tank. It's in the middle of both of our legs when we're sitting by each other. So I guess the difference they want you to know is that they have dual lines in our fuel selector, which is different than most of them. So normally we haven't even gotten to the diagram yet, so this is a little premature, but normally the fuel, when it runs through the system, will go back solely to the left tank, and they have dual lines, which means when the fuel runs through the entire system, it will go back to the tank that's been selected by you in the plane as what tank you're using. So I think it shows on here. Other aircraft have just the one line going off each right and left, and we have dual that come back and run through the system for the right and the left. But now we'll actually get into the fuel system itself. What time is it? It's 10. Do we need a break? Is everyone fading out right now? Okay. Tell me if we do. We're halfway through right now. Okay. Basics we need to know for the fuel system. This might be too basic because it seems you all have gotten like the gist of everything, but we have two fuel tanks, right? One in each wing. We have wing fuel tanks. They're located near the fuselage, so like in the root of the wing. As we just talked about, we can only select one tank at a time. Some planes have a both option to pull from both tanks. We only have left, right, and off. So one tank at a time is being used. Fuel runs through 3 filters. We're going to go through that when we go through the whole system. This is the page from the manual. I think the POH might have the same picture as well. We're going to have a simplified picture, so don't worry about that picture right there. But fuel enters from the right side of the engine and moves to the left and becomes pressurized through the pumps. So we're going to go for the actual. Okay. So left and right tank, right? So we have at the end of these tanks, right before they go to the fuel selector, like right at the root of the wing and the fuselage, they have an initial fuel strainer. It's basically like a spaghetti strainer. It's taking like any big rocks or debris or anything that's from the tank. It will stop that from going in. But as we know, spaghetti strainer is pretty big holes, so that's still anything contaminated like water will still run through and go to our fuel selector. So it runs through that initial strainer to our fuel selector where we've chosen which tank it's going to pull from. Next, it flows from our fuel selector to our gasculator, which is basically our second filter. It works as a filter. I think I showed everybody that did pre-flight with me on the plane what the gasculator looked like. Underneath there, you sump from the gasculator as well as the 2 tanks because of the second filter that it's being used for. It's the lowest part of the fuel system, like right under the nose of the plane, under the cowling. It's the lowest part of the fuel system, so we sump here to check for water because water is going to be heavier than fuel. It's going to pull towards the bottom, and then when we sump it, we're looking for that line. We'll see a line at the bottom of the sump that will show a clear separation line of water if there is water found in there, and it will be clear because water is heavier than fuel. So that's our second gasculator we sump from. That's our second filter after those initial strainers. Then we go to our fuel pumps. We have two of them. They are electrically driven. It's gonna work. That's pretty much the only difference between the fuel injected, the IS system versus the ULS system. The IS has two fuel pumps, and what the fuel pumps are doing is one, pumping the fuel through the system, and two, pressurizing the fuel. The biggest part of the electrical fuel pumps and the system itself is that we need pressurized fuel to run through our system, mainly because we're gonna get all the way back to our fuel injectors are pulling fuel from the fuel lines, and the fuel lines keep the fuel pressurized after the pumps. So fuel pumps pressurizing the fuel and pumping it through the system. From there, the two fuel pumps, we're going to our fine filter. This is our final filter. It's exactly what it says, a fine filter of debris and anything else that can be caught. And because this is such a fine filter, they have added a fail safe called the bypass plate, where if you have something in the fuel lines that is going to block the fine filter, that's going to block fuel from flowing to the engine, right? And we don't want any kind of blockage in our fuel system. So they've created this bypass plate that if for some reason this is blocked, all the fuel will still run past the bypass plate and to the engine. I keep pointing at this, but I need to use this. The bypass plate through to the engine, past if the fine filter is blocked. For some reason, if it's running through the bypass plate and the fine filter is blocked, it's probably contaminated, but contaminated fuel better than no fuel at this point. So that's why we have the bypass plate. An update to this system that they're not showing here that I'll point out, because if you look at your POH, you have a very complicated diagram of the fuel system in the POH. Has anyone looked in our POH at the fuel system? Okay, take a look now or after if you have the POH, but it's a pretty detailed, hard to read diagram. But one of the things that they added that wasn't in this PowerPoint or wasn't even there when I was training, but they've added a pressure sensor right after all of this, right before the engine. They've added a pressure sensor for the fuel right as it comes into the engine. It used to be a pressure sensor right after the fuel pumps because that's where the fuel is pressurized. But then they realized something might happen in between right after the fuel pumps and right before the engine. You really want to check, is the fuel pressurized right before it enters the engine, not right after it leaves the fuel pumps. So they've added a fuel pressure sensor right before the engine that tells us that the pressure is good before it enters the engine. Pretty self-explanatory, but just wanted to point that out. There's also another thing that they added in between like a second, or not even a second, we have two pumps here. They've added a boost pump, basically a third pump here right after it leaves the selector. You'll see that on the really complicated small diagram. The boost pump is doing exactly what it says. It's boosting, pumping that fuel to the gasculator and through the system. But those are two little things that are added that you might see if you checked.
So from the fine filters and pressure sensor that will tell it to go to the bypass plate then, or how does that?
No, it's going to be like the pressure sensor is going to be right here before the engine. It's basically checking that the fuel was pressurized correctly by the fuel pumps. It doesn't really have to do with the fine filter. The fine filter is just like straining any more contaminants that might be there. And by chance, if some contaminant like a rock or something gets through all of this and makes it to the fine filter, it's too big to get through the small, very small fine filter. So it will start blocking access through the fine filter for that fuel to go. And they don't want a chance for anything to block the flow of fuel. So they've added this bypass plate in case something gets through and blocks those tiny holes for the filter. Oh, it just moves forward. Like if it starts building up like here, it just flow. Yeah, it's just the back pressure valve. It goes back through. Not, yeah, a little more advanced than you need to know right now, but good to know any the less. But yeah, It's just gonna be another pressure valve that comes back, allowing the fuel to just run. Cause these lines don't actually, this is not actually what it looks like, in the engine. It's a little more precise in the POH, so it's not running there and then all the way back. It's kind of running two different lines, through it. And we'll go, yeah. So once we leave the fuel system itself, we start going through the engine. So like I said, it runs from the left to the right. If you're sitting in the cockpit and you're looking out on the engine, it's running left to right over here. Or if you're looking down on it on the top, it's running left to right. So cylinder 1 and 3 are on this side, cylinder 2 and 4 on this, and it's basically, there's a better picture here. This is showing you exactly that it runs back from the engine and goes back to the fuel selector. And based on whatever tank you have selected, it goes back to that tank that you selected instead of going back just to the left tank like other ones. I want to have a picture of what it looks like on top. This is kind of the best picture that we can look at, but right here is going to be our last fine filter. And right here is going to be the bypass plate. And it's going to run through here. I wish we had a better picture, but here and over here are our cylinders. And on top of the cylinders, is there any better picture? On top of the cylinders are fuel rods. Anything, okay. So basically on top of both these cylinders are going to be fuel rods, and the fuel rods are what the fuel injectors are connected to. So when the pressurized fuel runs through the fuel rods on top of the cylinders, it is the fuel injectors are able to pull minute amounts of fuel, or whatever it's calculated, through the ECU. It basically pulls those down from the fuel rod into the fuel injectors and then puts those into the combustion chamber through the intake manifold mixes. We went over how the 4-stroke system works, but there's a fuel rod on top of each of these cylinders, that when the fuel runs over it, the fuel injectors pull from that fuel that's running over it, and then it's pushed across a fuel line on the top of the engine, and then all the way over to the other cylinders where it runs across again, and the fuel injectors pull from the fuel rods on top of there. And then right at the end, I think it will show, I don't know what this is showing. This is not any correct, but basically all of the system that we showed, it's going to run, like we said, across the fuel rods, across the top, over the 2 other cylinders. And then there's a pressure relief valve right before it runs back to the fuel selector. So the pressure relief valve is obviously checking that the pressure of the fuel doesn't get too high. It really is not usual to have the fuel pressure be too high, but it's a fail-safe in case it's running too high. They have a relief valve that stops it before it gets back to the fuel selector. And that's what we'll see on here. So right here, 4 is the fuel line that runs on top of the engine. So this red part, it's going to be green in the plane when you look at it, but right here on top, those are the fuel rods underneath that like red casing. And then it runs over top in front of the engine to the other fuel rods, and then down here is the pressure relief valve. I think they have a better picture here. This is the pressure relief valve. After it runs over here would be the fuel rod. And then this box is holding the fuel pumps inside of it. It's back on the firewall. This is on the right side of the cowling when you open it. Here's the oil tank that you see. And right underneath it, on the wall, there's our fuel pumps. 2 of them encased inside there. Then we go to our air intake system. So our air intake, also on the right side, you're able to get a good look at this because it's that orange kind of like crunchy looking tube on the side. That's our air intake tube that's taking the air from the outside through that tube to our air box that sits on top in the back. I think there's an actual picture of what it looks like, but the air box is our air intake manifold. It comes inside the air box. There's a filter and it splits the air naturally. The air just flows through each of these to go through the actual manifold. I think it does like a little picture. Here we go. Here's the air moving through. Air gets split through the air filter in the splitter. And then it turns green apparently when it gets mixed with the fuel, with the fuel injectors. Oh, here's a great picture. Okay, so this on top is our fuel rod. So fuel rod over here, it first moves here across the fuel rod, over on top of the engine, moves on top of the engine, over to the other one, and then the pressure relief valves over here. So there's our prop on the front, just to orient ourselves. Our generator would be back here, and on top here where it says Rotax is our air box. So lots of things. There's the arrows that show how it moves. Oh, here's another good picture of it. Fuel rod runs across here, gets pulled down by the fuel injectors. I think it shows, yeah, gets pulled down by the fuel injectors. Yeah, calculated, very minute amounts of fuel are pulled in all the time from the fuel rods to combust and move the engine. Fuel pumps, so inside the little case that we saw in the other picture, this is what the two fuel pumps look like. And both, like we talked about, both are electrically driven, powered by the ECU. That's one of the three things that we talked about, the ECU powers. So anyone want to name, just please name the other two. So the ECU powers what three things? Fuel injectors and fuel pumps, perfect. And like I talked about, this is the point where the fuel becomes pressurized. All right, ULS fuel system, pretty much also very similar. Little bit of the same kind of thing, except the biggest thing is we have two fuel pumps, but they have one electric and one mechanical fuel pump. And in this system, the fuel is not pressurized. Because we have a mechanical fuel pump, you'll notice that too if you ever fly. Has anyone actually flown the ULS since we flew? Okay, perfect. Did you notice the fuel pressure in the plane is probably too early to actually notice this, but did you notice the fuel pressure was very, very low compared to other planes? It was like single digits. I think the fuel pressure was. Yeah. Okay, so did you notice the difference? Because it's like 40 in the IS, the fuel pressure goes up to like 40, and then in here, fuel is not pressurized, so it's like 5, I think, or 7, or something really low. Yeah, exactly. Yeah. Okay, I didn't expect you, but I was wondering if anyone noticed, but that's the biggest difference that we want to talk about here. We have a coarse filter that runs to the electric fuel pump, then to the mechanical, then to the engine. Andrew talks a little bit about this in his video in more detail too, but basically the mechanical fuel pump has never been known to fail ever. So it's pretty reliable for flying. A lot of people like the ULS because it runs all mechanical systems mainly compared to all electrical in the IS. But this is what we're looking for the main differences right now. Yeah, what we want to take away from today is the differences between the IS and the US or ULS fuel system and electrical system and everything. So main differences that we want to know are we've got one electric and one mechanical fuel pump, and the fuel is not being pressurized in this system. But of course it works the same way. Does I have another one? Yeah. It works the same way after the engine. It's pulled back to the fuel selector, and then it goes to whatever tank the fuel selector has selected. Fuel flow after the system to the engine looks a little bit different because we have two carburetors, right? We have two constant depression carburetors like we talked about. So each of those carburetors, like I said, is fueling or is flowing fuel to 2 cylinders on each side. Go from there. Okay. So it's pushing, it's the same system with the carburetor with the Venturi. We have that needle that's being mechanically choosing how much fuel we need through air pressure. And then it's sending that fuel to cylinder 1 and 3 for the first carburetor and cylinder 2 and 4 on the second carburetor. The air intake system is basically the same, except you have two carburetors, right? So it's coming still through the air intake to the manifold. The manifold air box is a lot smaller in the ULS. If you look inside the engine, it's not as big as the IS, but it also has an air box on top of the engine that has an air filter, and it splits that air into two lines that goes to each of the carburetors. Also do this, yeah. Goes to each of the carburetors, where the carburetor, as we know, mixes the fuel and air in the carburetor and sends that mixture to our combustion chambers and our cylinders. There's a little diagram of the, I guess this actually is what it looks like, but there's Andrew kind of plays with it. I don't know how to get to it, but it's a 3D model that you can kind of mess around with and look at everything of the engine. So this is our air box in the back. And then what are these pictures? This is your throttle mechanism. So when you push or pull on the throttle, it's going to pull this up or down to open the throttle. And then these are CDI boxes. I believe. I'm 98% sure these are CDI boxes. Now these pictures are the ones I don't know what we're looking at. I hate to say it, but I don't know what we're looking at here. So I gotta skip it because I don't want to give you the wrong information and guess on what that is, but I really don't know what those pictures were. So we'll move on to we already talked about this. One mechanically driven, one electrically powered. There's also that you can have leftover fuel in the case for the mechanical electrical fuel pump fail that allows like 30 seconds to a minute. This is also different, that it has a little leftover fuel in case the fuel lines, for some reason there's a blockage, you'd have leftover. This in the ULS. Cylinders, I feel like this is random going back to cylinders, but we're back. I'm not sure what he's trying to show here, but these are the cylinders. I think we know this. Here's a side view of the cylinders. We know this. What is this?
That's the stator.
Perfect. The stators behind here are generators, the generator. Here's a on top view of the engine. This our air box right here. Our two cylinders on each side over here. Here's our prop. Yeah, I don't know what this tries. I mean, up here you can see there's little fins on the cylinders. These fins cool the cylinders through the air that's running. You have these little nostrils in the front of the plane. That air that's coming in through the nostrils is running over. It's like a radiator that is pulling the heat away from the cylinders. That's about all I can give you from this picture. I'm not sure what it's supposed to be showing. Spark plug. Here's a spark plug. I feel like we already talked about this, but again, I did not make these slides, but we are doing the best we can. So we know each engine has carburetor or fuel has 2 spark plugs per cylinder, 8 in total. I guess I could have quiz, but yeah, here's what it looks like. You were wondering. Ignition, okay, ignition coils. We got a little bit into this yesterday, but like I said yesterday, it is taking that low voltage into high voltage needed to create that spark for the spark plug. Ignition coils are in the IS system. There's 4 ignition coils, and they control 2 spark plugs for different cylinders. Again, for redundancy, so if one of the ignition coils fails, it's not controlling 2 spark plugs for the same cylinder. So ignition coils are controlling 2 spark plugs for different cylinders, so that all of the cylinders are able to get power even if one of the ignition coils fails. Yeah. Purpose is to generate and send power to the plane spark plugs. I think we know this from yesterday. And yeah, not controlled by the ECU. Or the timing of the coils is controlled by the ECU, not the ignition coil itself. It's a middleman between the ECU and the spark plugs. ULS, we talk about the CDI, the capacitor discharge ignition system. We talked about this in the beginning. It's basically a magneto system. So I feel like we are good on these, like 2 small rectangular boxes. So that picture I showed, the 2 CDI boxes, that's what those look like. They mechanically time when each spark plug should be fired. So each box, if you go back to the electrical system, we have the generator, and you have half the generator. A and B is controlling 1 CDI box each. Each of those CDI boxes controls 4 spark plugs each. So, for example, A controls the bottom spark plugs for 1 and 3, and the top spark plugs for 2 and 4. So it splits it up again, in case one of them fails, that the other one is able to still give power to all the cylinders. Yes. Just like this. CDI A and B connected to each of the cylinders by 1 spark plug. Connected, connected, connected. Oil system. Okay, I think we have enough time to get through most of this. Okay, we talked about how we have a dry sump oil system. We know this because we have the tank, the oil reservoir, when we open the cowling, rather than having a pan at the bottom of the engine. They say it's for saving space. Okay, so no one can look at this. What are the 3 things that oil does for our engine? So, lubricates is 1. Who can give me another one? Cools is another one. Who can give me the 3rd one? Not hydraulics. Cools, cleans, perfect. Cools, cleans, lubricates. That was on this slide, so I put it back to the other side so no one can read it. But the oil system each plane cools, cleans, lubricates the engine and all the components of the engine. Like it's saying, pulled from the tank, runs through. Okay, we're just gonna look at the pictures. It's too many words. Come back. Here we go. Well, this is also missing a part, so don't draw this exactly how it looks. Oil reservoir goes through a radiator here. There needs to be a radiator on this diagram. The radiator cools the oil that's running through the system. Do we know where on the outside of the plane, when you look under the prop, you can see the 2 radiators? Do we know which one, the top or the bottom, is for the oil? Spencer knows a lot. Spencer?
It's the other one. It's the oil on the top, one's the bottom.
Yep. You can always think oil over water. So oil's on the top, that's our radiator. It's gonna cool the oil before it runs through our system. So radiator, when you draw the diagram in your notes, put a little radiator here before it moves to the oil pump. Oil pump is gonna push it through a filter before it runs to our engine and all the components to cool, clean, lubricate. All right, we'll keep going. Burping the engine, in case, just see if I didn't tell you what you were doing when you were turning the prop. You're pushing air into the engine where the oil rests, which is essentially the air comes from the pistons. As you're turning, it's moving the pistons, but it doesn't have anything in there because the plane's not on, so it's just pushing air. And that air is going to build up and push any sitting oil back to the tank, and that's when you pull the dipstick out after you burp it. Now it's pushed all that air's pushed the oil up onto the dipstick, where you're able to see now it's on its little line and where you have enough oil. Pictures, okay. 1, we all know this. This is our oil reservoir tank, right? Here, this is in the front of our engine. This is our oil pump. This is where it's connected to the camshaft, powered by the camshaft. The camshaft is back here behind it underneath the crankshaft. It basically spins at half the time that the crankshaft does. And there's some rods and we can get more into that, but powered by the camshaft underneath the crankshaft, oil pump. Then over here's the little filter that it runs through. And then these are the oil lines, I assume this is what they're talking about. Then we'll do engine cooling. Okay, now to the coolant system. The coolant system diagram is very almost exactly similar to the oil system, so it's pretty easy to understand. The sling uses water and ethylene glycol mixture. So we keep saying cooled by water or coolant or whatever. It's not the same coolant that's put in your cars, but it does a similar job. Yeah, we know because I'm sure there's a picture in here. Yeah, we know because we see this when we open the cowling. This is the overflow container, and then this is going to be the coolant tank over here. So we'll go back to the actual. I think this is also incorrect, which is great. Okay, so I'll redo this really quick for you. The coolant tank is going to first go to over here to the radiator, just like the oil system. So forget these orange lines. We're going to go from the coolant tank to the radiator. It does the same thing, cools it before it goes up here, I guess here from the radiator to the pump. Coolant pump is also powered by the camshaft, not the crankshaft. Camshaft is underneath. And then from there, it can go to the engine here. I don't know why we keep this, but any overflow from the system goes through the overflow line, because then it's going to come back to the tank. If the tank gets full and it's overflow, it goes back to the container. Does anyone know why we would have overflow with the coolant? I have a guess of why we need it. Ramon, I'm gonna give. Did you have an answer?
Well, if when the water or the cooling stuff will expand.
Exactly. Exactly. Water expands when it's heated up. It's the same with the coolant because we're using a mixture of water and ethylene glycol. So because when we start our engine, now we're creating all this heat. We want to make sure we have an overflow container because any heat is going to expand the coolant that we have. So we have an overflow container. It's the same with when you look at the overflow container in the back, we have this line at the bottom of where it should be like at least in the overflow container, because when we start the plane, it's going to be filled up even more. It's going to expand even more. So we can keep it pretty low in the overflow container because we know that's going to expand. And because this is the overflow container, we also have a whole actual tank elsewhere in the plane over here that actually is housing the coolant that's being used in the system. So this is just extra over here. Air cooling. So like we said in the beginning with the RANOG acronym, it's cooled by air, it's cooled by oil, a little bit of fuel was also cooling it, but air cooling is a lot of the sling system. So we use a lot of the cooling system is air. So this is how it kind of looks in the plane. At the front, we have those little nostrils, air intakes in the front. We have air intakes on the side over here. We also have an air intake on the side over here. And we have the two radiators in the front that are taking in air and cooling it when it comes through. So these are also cooling components for the whole system itself. I think that's all they're trying to say here. Oil continues. Yeah, oil and coolant temperatures are affected by the amount of air going through the radiator. So the same as we want, if something, the temperature on something is getting higher than you want it to be in the yellow, maybe even the red, that's why we turn the airplane, especially on the ground. If that coolant temperature comes up, you want to turn the plane into the wind, crank a little power if you need to get that air flowing. The propeller puts a little air back into as well, but you want to face into the wind, especially when you're doing it's on the checklist, when you're doing the run up as well. to get that air flowing in. We use a lot of ambient air coming in to cool the engine and all the components, so that's why we're doing that. Wow, a lot of words. I think this is everything we're talking. Intakes are small. Yeah, we have a lot of little air intakes, huge influence on our plane. Yeah, I just said during run up, really important to try to angle the plane into the wind. That's mostly going to be facing the direction we're taking off on the runway. A lot of the times, because of the ocean, we have a pretty direct headwind coming in on 29er. So you'll probably be facing towards where you're taking off. You can look at obviously the windsock to see where the wind's coming from, but a lot of times that's going to be coming right from the coast on the west. So you'll put your plane in that direction to get the most air coming in. Yeah, even if it's 100 degrees outside, airflow will cool it. So really important to be aware of how much air we're getting into the plane. Oh, I think back here, one thing with the, look at it, one thing with the oil. Yeah, one thing with the oil, this in the POH that they want you to know is the 122 Fahrenheit, the minimum oil temperature. So there's a lot of a lot of this you'll be able to see just in the green and the red on here, but they want to make you want to make special attention made to the 122 Fahrenheit or 15 degrees Celsius minimum oil temperature. You never want to be running your engine above 3,000 RPMs if that temperature hasn't come up already. So sometimes when maybe it's 7 a.m. when you're out there today, it's the first start of the plane today, maybe that oil temperature was low, same with the coolant temperature. You want to keep the plane running a little bit at around 2.5 before you bump that power above 3,000 to make sure you're at minimum oil temperature. That's important to how the plane runs. We want to keep everything. Okay. Fuel cooling, like I said, fuel's a little bit a component of cooling our plane because we constantly have this a little bit of a controversy of in all the slides, it says that we have 20 gallons of fuel constantly running through the system. People don't know where this came from. It's not in the POH. So just know that the fuel is constantly running through the system. As we saw, it's moving through the system and back from the engine, back to the fuel selector, back into the tank. It's constantly moving. So because fuel is constantly running, it's helping cool the engine. Yeah, the lines are wrapped in a fireproof insulator. Fuel lines in itself can heat up, so having constant flow of fuel is what helps cool down. Heating systems. So like we talked about with carburetor systems, you have carb heat to help, but we don't have carb heat and we only have cabin heat. There's also something called pitot heat for the pitot tube. We don't have that either. Cabin heat is what we have. It's a very weak cabin heat system. But you'll see that it actually looks like the knob for like a mixture knob or something. It's a black and you pull and push it open. It's very, very hot here, so we're not in need of cabin heat, but if we were,
Sorry, I don't want to interrupt. I'm doing like a little quick
Yeah.
announcement. I don't think I'm doing great to see you guys working so well. Sorry for interrupting you.
no, you're fine.
Just wanted to let you know that we're having a little community event in Santa Monica on Saturday. If you guys are around and want to join, Jake can tell more about it.
Yeah, it's community kickoff for the Santa Monica Airport. That's our first event there. We set community days, family days here on a regular basis, so this will be our first one there. So we'd love for everyone to attend. We put all the information on Discord, and I'm putting some in this slide.
Just a fun little low-key event, casual, explore a different airport. Love to see as many of you there as you can. Sorry for interrupting.
No
Yeah,
problem.
sorry about the mess out here. I don't know, but should be all cleaned up on it. Thanks everyone. See ya. Thank you.
Yeah. Cabin heat, maybe you'll use it in the winter. It's has a, I think they show back here in our actual plane in the back by the firewall, you can see it's this little box that kind of is gold. And it has a lever that's pulled, so if you look, if someone's pulling it inside the plane, it opens and closes this valve right here to let in basically ambient heat coming off the muffler goes through a tube which leads to the cabin. So before into the cabin goes through a box. That's the box that they just showed in the picture. And that's where the lever inside controls how much is being let inside. Obviously, there's risks with cabin heat, because it's coming from heat from our exhaust. So if there's an issue, we'll get into this in human factors a little bit when we talk about carbon monoxide poisoning, but it's an issue with if you have a crack in the exhaust pipe, now you're letting in exhaust fumes into when you open the cabin heat. So just be aware of that. It's a minor risk, and I would say almost never are you using the cabin heat out here, but it's good to know that we have this system in the plane. Yeah, carbureted slings are given the option to have carb heat. And as we're not allowed, does everyone know that because we're light sport, we're not allowed to go into IMC conditions, instrument meteorological conditions? I'd assume they told you this on like NDOC or something in the beginning, but when you get to instrument flying, they're working on it right now to get them certified to fly into IMC because we can. We have all the instruments. We have a fully certified instrument panel. We're able to go into IMC, we're just not allowed to go into IMC because we are certified light sport aircraft. So yeah, because we're not going in IMC, a lot of the planes don't have carb heat because it only adds more weight to the plane. So I don't know if specifically if the Tango whiskeys that are on the line right now have carb heat, but it seems like a lot of them have been removed to save weight, so I would assume not. Battery. Okay. Electrical buses. This is new to the PowerPoint because back in private, I didn't know anything about electrical buses. We kind of moved past that, but in the electrical part of the POH, it has a very expanded diagram of this that you can look at. But what we mainly want to look for when we're looking at the electrical buses is that the battery is powering what we call down here the main bus. When we're talking about electrical buses, so the battery we know is charging the G5 backup battery. We know it's charging the avionics for our GTN 650. It's powering our autopilot. It's powering the G3X. We also have the battery powering what's called the main bus down here, which means lights, ELT, transponder, trim, and flaps are all under the same electrical bus, which means if you turn the master off, all of them are not usable. So that's what we're getting to. You can look at it in the POH. It has it labeled as the main bus, but that means that all of these are connected to the same electrical bus, meaning if you lose power to one of these, you lose power to all of these at the same time. And then we see that the battery is also taking the load of all these other components, but I think that's what they're getting at during this. And then starter system, we're going all the way back to the beginning, talking about when we start the plane. So we have to the picture. We have very small starter motors in the plane. So what's happening when you're turning the key is that the starter motor is starting that crankshaft. So you can start generating power through your generator. The crankshaft starts spinning, the magnet in the front starts spinning, you're getting power from your generator. That's how we start the plane. So that initial turn of the key is starting the little starter motor to get the crankshaft moving, to get the generator moving and those magnets to create power. So I think what they want to get to here is that when the starter motor can only do so much. Once the generator is started with that starter motor, and it starts creating power, that initial generator power is sent straight to the ECU. Because we need to start our engine, right? So all that power is initially sent straight to our ECU to get our engine running. Then when we get to, does it have a thing on me? Yeah, it takes a huge chunk of battery power and a larger gear. So basically the starter motor is spinning a really small gear that's connected to a bigger gear, that's connected to a bigger gear, a whole gear system. And that gear system is what starts turning the crankshaft that starts the generator. So what they want you to know, this is exactly what I just said, spins the crankshaft, rotates the magnet around the stators, generates power. So it starts charging the battery, but only at a certain point. Did we get to that here? No. I think we'll get to that in abnormalities, but when you're doing the generator through the starter motor, it's sending all that power to the ECU to start the engine. And it's only when you increase the RPMs to 2,500 or above does it click on generator B to start powering the battery. I think we'll get to that later in the presentation, but since we're starting with the starter motor, it's important to know that it's part of the checklist. It says specifically put the RPMs to 2,500. That's so we can get that generator B switched on and get the batteries charging. It's also so that we can equalize the power that the generator is creating. It can't all, even if we only have generator A turned on for the ECU, it's only giving, or it's still generating all the power it needs to give to the battery as well. So this is how you fry the stators and fail the generator over time. It basically melts the wires around the generator if you don't put it to 2.5 immediately when you start up to get that generator B going, because it's creating all this power. It's only using some of it for the ECU. And if you stay at 2,000, it's going to keep creating all that power. It has nowhere to push that to charge the batteries and turn everything on. So all that ambient heat that's being created is going to eventually fail the generator because the wires are going to melt. Okay, back to generator failures. All right. Generator failure. So what's smart about the plane is that it can reroute the power that it needs. So if generator A fails, and that powers the ECU, right? It's not just going to cut your engine immediately. It's going to reroute. Where does it show? It's going to reroute, there it is, generator B to rectify regulator A to power the engine, because that's the most important, right? We don't really care about the battery at this point. We want a running engine. So for some reason, generator A fails, it's going to reroute generator B's power to rectify regulator A and over to the ECU. In the ULS, if you have a main generator failure, that's going to cut the battery, but that's why we have CDIA and CDIB on the ULS, because CDIB will be able to still power the engine. It will be less power than it's able to create with both, but that's why we have redundant CDI and CDI B and A, so one can take over the other. So the ULS is pretty simple, but the IS, so normal engine indications. This is what looks normal, right? We have, say we're cruising 5,000 amps, 0 volts, about 13.5, 13.7. This is normal in cruise. Now we're going to look at what looks abnormal. What we're looking at when the start of a generator failure is going to be slow, but there will be indications. If a generator fails, it won't immediately cut off your engine. You're going to see a slow trend, but this is where you're looking to notice the generator failure, your volts and your amps. And that's going to be when you open your engine page on the bottom, next to your fuel indicator. So you're going to have volts and amps next to that. This when you're starting. So this is what I just talked about. You turned that starter, you engage that starter with the key. It's gonna look like this inside the plane initially, because you're at 2,000, generator B is off. It's still putting power to the engine, but no power to the battery. So this is what our electrical system looks like when we're kept at 2,000 after the start. Then, when we bump it up to 2.5, like I said, then that's when our amps come up, our volts come up in the green, and this is good start indication that we're working. Amps won't stay at 6 because after that, we're gonna turn in all our lights, turn our avionics on, turn our autopilot on. All that's gonna be pulling from the amps. The amps is basically the charge of the battery. The amps is showing the charge. So if we're at 0, that means it's producing enough power to charge everything. That's equilibrium. Everything is being charged, but it's not creating any extra charge. +6 is going to be an extra charge on top of powering everything. That's why when we turn on avionics and autopilot and all those other switches after we start the engine, it goes back down to like +1, 0, something around there, because now it's pulling all that charge that the battery had to all those instruments or panel that we're using. So big part of normal indication to know is that amps is the charge that you're looking at with your battery. And volts 1 and volts 2. Volts 2 is going to be your charge of the backup battery. So it's a little less important. It's your ethos battery. But we still want to take a look at this volts. Volt 1 is also indicating the charge of the battery. So this is the one that we really want to look at. Both of these volts 1 and amps is going to be our first indication of a generator failure. You're going to see amps go into the negative, into the red, and you're going to see the volts 1 also start dropping towards like 12, 11, something around there. That's indicating you have a full generator failure. But we'll get into what actually is concerning and what's a complete like emergency. You're going to lose your engine. Yeah, initial signs of a generator failure. This is what it'll look like. Initial, very, very beginning of a generator failure, you'll notice the amps go into negatives. Now, Andrew talks about this in his video too when you watch it. It's -1 and -2 are not super concerning. You don't need to be preparing to do an off-field landing with -1 or -2 amps. -1 or -2, you're fine. You just need to keep monitoring that the volts also don't drop below. They're indicated about 13.5, 13.7 is usually normal. But this right here, -3 and anything below is okay, I need to be watching, something's happening. And what's the first thing we can do? If this is all the charge of the battery, what can we do if we see negative amps? That's indicating, okay, now we're getting less charge than we need to power everything. What's a way that we can help to stop the generator from failing? Yes,
You turn stuff off.
exactly.
They don't have any pop breaker.
Exactly. Shed load is what you'll hear a lot. Shedding load, mainly the lights. The lights take a lot of power from the battery. And legally, we don't need the taxiing the landing light on in the air. We have them on in the checklist just for situational awareness to have more lights on, I guess, but we don't need those. So immediately when you see this, shed load and increase power. So immediately we're turning off our landing and our taxi light and we're increasing power. And then we're gonna look, monitor, okay, do our amps come back up into 0, maybe +1? Then we're okay. Then you can keep flying, maybe head back towards the airport, but it's not, if you can fix it with shedding load, we're okay. Continue normal flight, just maybe head back towards the airport so you can get maintenance to have a look at it, but you're not gonna lose your engine. The problem will be if you shed load, you see this, you turn off some of your lights, you increase power and it stays at -3 or continues to drop, or you start to see this volts 1 drop as well. Then we have a problem. Then you want to be looking for this power increase with load. So this is what we're shedding load and we're increasing power. The increase to 5,300 and then the amps were brought back to 0. This is okay to continue with normal flight. We don't need to be doing an emergency landing or trying to restart. This is a full generator failure indication. This is, you're at full power. Maybe you shed some lights, shed some load on the lights, and you've got -8 amps and your volts. One is at 12.4 in the yellow over here. This is indicating something is seriously wrong and you have a full generator failure, which means the battery that is, you're gonna lose your battery first, and then that anything the battery has left will transfer to the ECU, and then you'll lose your engine after that. Yes,
Also turn on other things other than lights.
yes, no. If you get this indication of a full generator failure,
Yeah,
you're going to, one, turn to the nearest airport, start
Yeah.
getting yourself there. Two, because like I said, this happens gradually. This indication doesn't mean in 2 seconds the prop's gonna stop spinning. This means you need to prepare. So like you said, turn off basically anything, literally anything, except for your 2 lanes. Anything that's in the red, your 2 lanes and your 2 fuel pumps will keep your engine on for as long as you can. I'd rather have my engine than have my avionics and moving map and radios. So if you can, first, before you turn everything off, maybe get on the emergency frequency and make 1 call and then turn everything off and head towards an airport.
Yeah.
Maybe turn the squawk code on for an emergency so they know something's wrong with your plane, because after you turn everything off, avionics, you won't have radios. You won't be able to communicate with tower or anywhere you're coming into. So before, if you see this, I might, just for safety, try to make a call really quick to let someone know that you're having an emergency. You'll be heading to the nearest airport so they can clear traffic off the runway. Then turn everything off except those fuel pumps and those lanes. Those will keep your engine going for as long as possible. But this is impending failure, so it will keep it on as long as possible. It will quit if you're not like immediately at an airport. It will continue to drop. That battery is already at -8. It's got no charge. It's running off of whatever's left. And rerouting that to the ECU for whatever engine power you have left. And then what we have in the plane, I don't know why there's not a slide on this, maybe it's later, but we have a ECU backup, right? If you're doing your run up, or doing your start, you've noticed that you turn that on and turn it back off, when you're starting the plane. ECU backup is used for when the prop has stopped. If you see this and you're trending down, but your prop is still spinning, you still have an engine, don't turn ECU backup on immediately to try to keep it going, because you're just pulling more power from this ECU backup battery. This battery is for when your prop has completely stopped. This is a last stitch effort to start the prop again. So once the prop is stopped, follow, emergency procedure where you're pitching for 72, still make a turn towards your nearest landing spot, and then turn ECU backup on and restart the engine. That battery backup is going to give a little bit battery back when you restart the engine. That can give power back to your engine. They say it gives you 30 minutes. I wouldn't rely on 30 minutes. I would 15 minutes, get to your nearest airport and land, but that's what the ECU battery backup switch is for. In this case, like we were saying, make a call, turn everything else off and keep the engine as long as you can, especially if you're flying in the mountain areas, like on a cross country. You want to keep the engine on as long as you can and wait till it completely dies and then turn on ECU backup, try to restart the engine and fly as far as you can on that. Get to the closest airport that you can. They think they should get to this at some point, but we're like right at the end of class. I want to see how. Where are we? Oh boy, we have a lot more. Oh no, wait, this is the rest of, this is how an engine works. So we only have a couple more slides. This isn't bad, okay. Okay, enough for today. I've talked way too long. You're really sick of my voice after all this, but tomorrow we will finish the rest of these slides. Look over the POH, watch the video if you want. He's way better at explaining all this than I am, so watch the video. Come tomorrow with any questions you have about systems, to get out of the way, any clarifying questions, any questions from the video. Look at your POH, that's where the most important systems information comes from. That's your reference in a check ride and a phase check to all the system information, so be able to have that reference when you're talking about any of this. And then we'll finish that and then we'll do a little quiz tomorrow. After that, and hopefully get out early, because I've kept you till the very end every single day. Okay,
Slides on the Discord.
oh yeah. Go to. Yes. Resources.
Whereas you're passing now. Oh, one is. Or. Maybe no tomorrow gonna go on.
Okay, under information, I have resources. Okay, well, you know, I said, so basically this is getting. Dot sling file, time we're done. And that's gonna be student hub and then go to ground instruction, PPL, and it has all the links.
Okay.
No problem.
I'll have a question.
Yeah.
One